Up to now, we've tended to look at the effect of a single applied stress on a mechanical or structural part. In this first part of Chapter 12, we will focus on the action of more than one stress on a component. Let's consider the stresses acting on a bolt. In Chapter 5, we focused on the shear stress in the bolt that occurs horizontally in the x direction at the shear plane, where the two plates touch. The upper plate is being pulled to the left, while the lower plate is being pulled to the right. A shear stress develops in the bolt equal to the load P divided by the cross-sectional area of the bolt. There are other stresses that develop in the bolt. If the bolt is tight, then there's a tensile stress in the y direction along the shank of the bolt. Friction between the bolt head and the upper plate and between the nut and the lower plate means that there will also be a torsional stress in the bolt. Bending and shear stresses develop in the head of the bolt because the head wants to stay put while the shank wants to pull downward. There are shear stresses in the threads of both the nut and the bolt acting in the y direction. It looks like a pretty simple device, but a bolt has to support a combination of many stresses in different directions. Let's consider a beam that's loaded in bending, but it also has an axial tensile load. We'll use a 2x4 timber that's 8 feet long. We can use the principle of superposition to solve this type of problem. First, let's consider the bending stresses only. We have a point load acting at the midspan, so Appendix F tells us that the maximum moment is PL/4. You could instead draw shear and moment diagrams to calculate the maximum moment. The bending stress is maximum at the top and bottom of the beam and 0 along the center line. We're only interested in the maximum values because if the strength of the beam is exceeded, failure will begin where the stress is highest. Bending stress equals mc over I, or m over s. We can look up s sub x for a 2x4 in Appendix E. Substituting the mmax equation into the stress equation gives us stress equals PL/4s for this particular loading case. If the loading were different, we'd have a different result. Solving for maximum bending stress, we get a compressive negative 784 psi on the top surface and a tensile positive 784 psi on the bottom surface. Now we'll consider the axial tension load only. This is a simple P over A equation, and the stress is positive. Superposition allows us to add up the stresses due to each separate loading. Along the top of the beam, the total stress is a compressive negative 670 psi, and along the bottom of the beam, the total stress is a tensile positive 898 psi. You can look up in Appendix E to find out whether the beam is safe. The allowable bending stress is 600 psi for eastern white pine, 900 psi for Douglas fir, and 1400 psi for southern yellow pine. Based on this information, the beam would fail if it's made of eastern white pine. It's right on the edge of failure if it's made of Douglas fir, and it's plenty strong enough if it's made of southern yellow pine. Here's a beam with two bending loads. One load is vertical, while the other is horizontal. They're both acting at the midspan, which makes the math a little simpler. The gray box shows a cross-section of the beam where the loads are being applied. We're going to use the principle of superposition to calculate the combined stresses at the edges of the beam, which are the corners of the gray square. From Appendix F, when the point load is at the midspan, the maximum moment is PL over 4. The moment about the vertical y-axis is the horizontal load times L divided by 4. And the moment about the horizontal x-axis is the vertical load times L divided by 4. Bending stress is moment divided by section modulus. Let's split the problem into two problems, calculate the bending stress at each corner point for each load, then add up the stresses to find the combined stress values. Consider the vertical load first. Bending stress is positive, or tensile, along the bottom surface, and it's negative, or compressive, along the top surface of the beam. If we plug in some numbers for P, L, and S, we can calculate stresses at the 4 points due to the vertical load. Now consider the horizontal load. Bending stress is positive, or tensile, along the left face of the beam, and it's negative, or compressive, along the right face of the beam. If we plug in some numbers for P, L, and S, we can calculate stresses at the 4 points due to the horizontal load. The last step is simple addition. Set up a table with the values, then add them up to find the total stress. These numbers are pretty small for a structural material, but let's imagine that our beam is a stick of butter with a strength of 12 psi. If we only loaded it with the vertical load, it would survive, because the maximum stress is only 10 psi. If we only loaded it with the horizontal load, it would still survive. But with both loads in place, the maximum stress is 18 psi, which exceeds the strength of the material, and the beam will fail. The third example of combined stresses involves an eccentric load. In our previous problems, tensile and compressive loads have been lined up with the centroidal axis of the component, but in this case, the load path takes a jog. Let's pretend that a heavy traffic light hangs from a weightless arm and a weightless post. We want to know what the stresses are at points A and B at the base of the post. There are two components to the stress. There's the axial stress of minus P over A, where the area is the cross-sectional area of the post. It's minus because we have a compressive load. Then there's the bending stress of mc over I, where I is the moment of inertia of the post. In an eccentric load problem, m is P times E, so the bending stress is plus or minus PEC over I. It's plus on the tensile side, which would be point B, and minus on the compressive side, which is point A. Add the two components of stress together to get the combined stress. The drawing at the right is basically an equivalent load diagram showing the axial load as P and the eccentric load as a bending moment. The weight of the traffic light is making a cantilever beam bend to the left. Of course, in the real world, the arm and the post also weigh something. Now we have two eccentricities, one for the lamp, the other for the arm. There's no eccentricity for the post because the weight of the post runs along its centroidal axis, so E would equal 0. The axial component of stress includes all three weights. The fourth example of combined stresses is an eccentric load of a chain link. It's being pulled by pins inserted into two holes, but the main body of the link has a different shape. We want to know the stresses at points A and B, so what we do is cut the link at the section where A and B are located. Now we have an eccentric load problem, where the eccentricity, E, is the distance from the axis where the pins are to the neutral axis of the center portion of the link. The values of C, A, and I are also taken at this cross-section. In this problem, the P over A term is positive because the link is being pulled. In the previous problem, the P over A term was negative because the post was being loaded in compression. So this completes the first part of Chapter 12. In the second part of Chapter 12, we'll look at eccentric loading of short masonry blocks loaded in compression.